So now we will start the new topic, which is also important for get point of view. That is availability and irreversibility. Availability and irreversibility. Irreversibility. So now we will discuss some of the fundamentals for availability and irreversibility. So first of all, we will define the available energy and unavailable energy. So for available energy, that is the maximum work output, the maximum work output, work output, the maximum work output obtainable obtainable from a given heat engine given from a given heat input in a cyclic heat engine in a cyclic heat engine is called available energy is called available energy. So I am again defining the available energy, that is the maximum work output obtainable from a given heat input in a cyclic heat engine is called available energy, or we can say that it's a available part of the energy supplied. Similarly, we can also define unavailable energy. Unavailable energy. So for unavailable energy, we can define as the minimum energy, the minimum energy, that has to be rejected, that has to be rejected, to the sink by the second law, is called unavailable energy. Is called unavailable energy. It's called unavailable energy. So first of all, I will draw the heat engine, and then we will describe the mathematical formula for available and unavailable energy. So here I am talking about heat engine. This one is source T1, and this T1 is source is supplied Q1 to the heat engine. Operating in a cycle here, and it is rejecting amount Q2 to the sink, which is at the temperature T2. So the available energy means the maximum work output, that is available energy, and the minimum heat which are rejected to the sink, that is called unavailable energy. So from cyclic point of view, or from this diagram, it's very clear. It is W max is our available energy, and Q2, which is rejected to the sink, it is unavailable energy. So now I can write Q1 is nothing but summation of available energy plus unavailable energy. So for W max, I can write that is available energy equals to Q1 minus unavailable energy. Q1 minus unavailable energy. So now we can define the available and unavailable energy in a cycle. Now let's define available and unavailable energy for a process. So now we define available energy and unavailable energy, label energy for a process. For a process. So here I am just drawing a process on TS diagram. On y-axis I will represent T. On x-axis I will represent entropy. So this one is the process XY, XY here. And in this process we are supplying the heat, that is QXY, supplying the energy QXY. And for this process we are having two parts, that is available energy and unavailable energy. So here in this part, whatever I am showing by dotted line, that is unavailable energy, unavailable energy, that is nothing but product of ambient temperature and the change in entropy from X to Y. And this part is called available energy. Available energy, it is nothing but the maximum work. It is nothing but the maximum work. So now I will define the available energy and unavailable energy for this process. The unavailable energy, the unavailable energy, unavailable energy is the product of the lowest temperature, product of the lowest temperature, lowest temperature of heat rejection, lowest temperature of heat rejection, and the change of entropy of system, and the change of entropy of the system, change of entropy of the system. So unavailable energy I can write T0 Sy minus Sx. So by this way we can calculate the unavailable energy. So we are having two more terminology for available and unavailable energy. So first of all I will define the available energy. So we have already defined unavailable energy. Now we will define available energy. So available energy is nothing but the maximum work output. So the maximum work output we can define Qxy minus T0 Sy minus Sx. So by this way we can calculate the available energy. So the other terminology for available energy and unavailable energy I am writing here. The available energy is also known as exergy. The available energy is also known as exergy. Available energy is also known as exergy, and unavailable energy is also known as energy. And unavailable energy is also known as energy. So that is one more terminology for available and unavailable energy. In the available and unavailable energy, I will write down some of the important concepts in field of availability and irreversibility. So now let's take reversible work. Let's take reversible work by an open system exchanging heat heat only with only with surrounding exchanging heat only with surrounding. So here we are interested in the maximum work done. So I am writing just the formula for maximum work done in that case. So dW max in that case will be dm1 h1 minus t naught s1 plus v1 square by 2 plus g z1 minus of dm2 h2 minus t naught s2 plus v2 square by 2 plus g z2 minus of d u minus t0s plus mv square by 2 plus mgz. So this one is the formula for reversible work by an open system which is exchanging it only with the surrounding. All the notations we have already discussed during the discussion of steady flow energy equation. Here the number 1 is representing initial stage, number 2 is representing final stage, and whatever the representing by 0, that is called ambient condition. So the above equation is the general expression for the maximum work of an open system which is exchanging heat only with the surrounding. Now let's take another important concept, that is reversible work in a steady flow process. Reversible work in a steady flow process. Steady flow process. So I am just writing the maximum work done for a steady flow process here. So the W max in that case is H1 minus T0 S1 plus M V1 square by 2 plus MZ Z1 minus of H2 minus T0 S2 plus MV2 square by 2 plus MC Z2. So here there is a very important function here I am defining. The H minus T0S is called the Kinon function. So remember this thing, sometimes in GATE they are asking about the function. Kinon function which is representing by B. So H minus T0S is called the Kinon function and which is representing by B. So now if we put the Kinon function in the above formula, we will get W max equals to B1 plus MV1 square by 2 plus MZZ1 minus B2 plus MV square by 2 plus MZZ2. So here we can also write psi1 minus psi2. W max in case of reversible work in steady flow process, that is W max, we can write psi1 minus psi2. So psi is availability function of steady flow process. So now we can define the psi is nothing but B plus, that is Kinon function, mv square by 2 plus mgz. So Kinon function is important as well as the steady flow process, the availability function psi, that is nothing but P plus mv square by 2 plus mc set. So now I will define the important terminology that is useful for. So remember one thing, whatever work that done by the system is not available for delivery because some of the work will be spending in pushing the atmosphere because there is a atmospheric pressure, so against which we have to do some work, and then this work done will be available for the delivery. So the useful work is not a maximum work because whatever we are getting is a maximum work. Then we have to subtract with this work done against atmosphere, and now this work will be useful for uh, doing the other things. So I will define the useful work that all the works W, all the work W of the system, W of the system would not be available, would not be available, would not be available for delivery, since a certain portion of it, since a certain portion of it would be would be spent in pushing out the atmosphere, pushing out the atmosphere. The useful work is defined as the useful work is defined as is defined as the actual work delivered by a system, actual work delivered by a system less the work performed on the atmosphere. The work performed on the atmosphere. The atmosphere. So now suppose V1 and V2 are the initial and final volume. Let V1 and V2 are initial and final volume. Initial and final volume. Final volume. And P0 is the atmospheric pressure. And P0 is the atmospheric pressure. So the work done on the atmosphere will be work done on atmosphere will be P naught into V2 minus V1, then useful work will be plus 2, it is denoted by WU plus 2 W actual minus P naught V2 minus V1. So similarly we can write for maximum useful work also. So maximum useful work which is denoted by WU max will be W max minus P naught V2 minus V1. So this equation, that is W max minus P naught V2 minus V1, generally used in case of closed system because closed system has to work against the atmosphere. So I can write for closed system. And in case of open system, there is no change in the volume because open system there is nothing like work against the atmosphere. So the volume is not changing in case of open system. So in case of open system, the useful work, useful work is actual work means we can write WU equals to W actual, or in terms of maximum work also we can write WU max equals to W max. So in case of open system, because in open system there is no change in volume. So now we will discuss the maximum useful work for the closed system. So we will discuss maximum useful work for closed system. For closed system. So for maximum useful work for closed system, we are having the formula, that is E1 minus E2 plus P naught P1 minus P2 minus T naught S1 minus S2. If kinetic energy and potential energy changes are neglected, then WU max, that is maximum useful work, we can write U1 minus U2 plus P naught V1 minus V2 minus T naught S1 minus S2. So again I can rewrite this W max equals to Q1 minus P naught V1 minus T naught S1. U1 plus P naught V1 minus T naught S1 minus U2 plus P naught V2 minus T naught S2. So again I can define it's nothing but phi 1 minus phi 2. It's nothing but phi 1 minus phi 2. So here phi is called availability availability function for a closed system, for a closed system. So I will again define phi is the availability function for a closed system, representing by U plus P naught V minus T naught S. So the availability function for a closed system is denoted by phi, and it is equals to U plus P naught V minus T naught S. Now we will define the one more important function, that is Gibbs function. So I will define here the Gibbs function. So the Gibbs function is defined as Gibbs function is denoted by G, is defined as G equals to H minus Ts, or sometimes in place of H I can write U plus PV minus Ts. This one is the Gibbs function. So remember this thing. Sometimes in objective questions they can directly ask about the functions. It may be availability function for open system, it may be availability function for closed system, or it may be Gibbs function. Now I will talk about irreversibility. It is also important. Irreversibility. So now we will discuss some of the things regarding irreversibility. In the last chapter, we have already defined the types of irreversibility, that is internal irreversibility, external irreversibility. So now we will talk about the definitions of irreversibility and how we can calculate it. So in real situations, the actual work done by the system will be always less than the idealized reversible work. And so the difference between the actual work and the idealized reversible work is called irreversibility. So I am writing here the definition for irreversibility. The actual work, the actual work done by a system, done by a system is is always less than the always less than the idealized idealized reversible work, reversible work, and the difference between the two, and the difference and the difference between the two, the difference between the two is called the irreversibility of the process. Is called the irreversibility, irreversibility of the process, of the process. So in mathematical term, we can write irreversibility that is denoted by I equals to W max minus W. So this is also called degradation or dissipation. So this is also called this is also called degradation, degradation or dissipation, dissipation. It is also called degradation or dissipation. So now I will give the formula for calculating the irreversibility. So for calculating the irreversibility, there is a very simple formula. I am writing irreversibility, irreversibility that is denoted by I equals to T naught into change in entropy of system plus change in entropy of surrounding. So now for calculating irreversibility, we have to sum up the entropy change for system and surrounding, and then we have to multiply it with ambient temperature. So for simplified form, I can write T0 del S system plus del S surrounding is nothing but universe. So I can write del S universe. With the help of this formula, we can easily calculate the irreversibility. Now we will talk about a very important theorem that is called Stodola theorem. So I am writing the theorem here, the Stodola theorem. So according to this theorem, the rate of loss of available energy, I am writing here, the rate of loss of available energy, available energy or exergy, because available energy we can also call exergy in a process, in a process is proportional to is proportional is proportional to the rate of entropy generation. The rate of entropy generation, which is denoted by S dot gen. So in mathematical form, that is I dot equals to W dot lost equals to T0 del S universe dot equals to T naught S gen dot. So this one is the Stodola theorem.